start करते हैं तेरे करने कुछ चीज़ नहीं देखी जो start स्क्रीन कुछ so what we'll do today is we'll discuss about polarization of electromagnetic waves. So remember, this is polarization of electromagnetic waves, not the polarization of the material. Polarization of material you have studied earlier, in which case you must have seen D is equal to 1 plus xi E, xi is equal to then and that is equal to epsilon 0 into epsilon E. That takes care of the polarization in the material. When you apply electric field to a material, then the electrons within the material, they try to align along the electric field. So it is not that. This will be, and what we are going to discuss is the polarization of the electromagnetic wave. And for that, we consider here, when we say the polarization of electromagnetic wave, we will be considering plane monochromatic wave. Remember, plane monochromatic wave propagating in isotropic homogeneous medium. Total discussion that we are going to do is for plane monochromatic wave propagating in isotropic homogeneous medium. For that, we are going to discuss what is polarization. We will define polarization and find out what is polarization and see the analysis of polarization. Now, in a plane monochromatic wave, electromagnetic wave, when we consider electromagnetic wave, in a plane electromagnetic wave, which is monochromatic, we have two types of field. One is the electric field, one is the magnetic field. Both these fields lie in one plane and they are perpendicular to each other. So E and B, they describe a plane wave. When they describe a plane wave, they are in one plane and they are perpendicular to each other, and this plane is propagating in a direction which is perpendicular to the plane, and that direction is the direction of propagation of the plane wave. And these waves, being monochromatic, have a time variation of the form exponential j omega t. This much we know. And we have discussed about plane electromagnetic waves earlier in the last class, earlier classes. So we are not going into that. From those concepts, we will develop the concept of polarization. So to start with, E and B, they describe a plane wave. E is the electric field, B is the magnetic field. They describe a plane wave. And when we discussed about the plane electromagnetic wave, we saw that there is a definite relationship between the magnitudes of E and B. Actually, they differ by a factor of C, where C is the speed of light. E is equal to C times B. That is what we have seen. So magnitude of E is equal to C times B. So they are related, their magnitudes are related. Then we also saw that they are orthogonal to each other in the plane that contains E and B. In that plane, E and B are orthogonal to each other. Since they are orthogonal to each other, E dot B, or their scalar product, will be equal to 0. So now we know two things. The E and B are their magnitude, the relationship between their magnitude and their direction, because they are orthogonal, so that we know. Their magnitude we know, which means if we know only E, we can find out what is B. If we know what is B, we can find out what is E, because once we know B, we can find out what is the magnitude of E and what is the direction of E. Similarly, if we know E, we can find out what is the magnitude of B and what is the direction of B. So if behavior of one of them is known to us, either E or B is known to us, then we can find out the behavior of the other one. Now, then also we know that these plane waves are dependent on time and space. So they are spatio-temporal waves. So they depend on space and time, both space and time, which means at a fixed position, if they are dependent on space and time, so let us fix the position, which is the space. If we fix the position at a fixed position, these vectors will move with time. Similarly, at a fixed time, these vectors will vary over space. So this is what is meant by they are dependent on time and space. Now, with this knowledge, we can say knowing one of them is sufficient, and since E is sufficiently larger than B, therefore knowing the variation of E or the electric field is enough. Once we know how the E varies, we can find out B. Therefore, throughout our discussion, we will concentrate only on E. Now, when we say that, this means the polarization, from that we will come to this definition. The polarization will describe the variation of E at a fixed position. So we fix the position because E depends on position and time, or space and time. So we fix the position first, then vary time, and then vary time. If we do that, then polarization describes the variation of E or the electric field at a fixed position with respect to time. How do you define the polarization? We define the polarization at the locus of the tip of E, the locus of the tip of E with time. So as time progresses, as you go on increasing time, so over one period, one complete period, whatever locus is described by the tip of E, E is a vector, electric field is a vector. So vector will have a direction. The direction we describe by an arrow. So the tip is the arrow tip. So that arrow tip, whatever locus is describes, or the curve with the arrow tip describes, that curve is called the polarization. If that curve is a straight line, we call it a linear polarization. If that curve is an ellipse, we call it an elliptical polarization. If that curve is a circle, we call it a circular polarization. So the locus of the tip of E gives the type of polarization. Now let us come to on the E. We are going to concentrate only on the electric field. The general solution for the electric field in a plane wave will be of the form E. E is the electric field, which is a real quantity. Therefore, E is equal to real part of E0, E0 being the amplitude, into exponential j k dot r minus omega t. J k dot r gives you the spatial variation, and j minus j omega t gives us the temporal variation, or the variation with time. This we have already derived from the wave equation. The solution of E is in this form. So we are going to use that form of the solution. Now what is in this case, E0 is the amplitude, but it can be a complex vector. Now we'll see how it will be a complex vector, but E0 is the amplitude. It is a complex vector in general. Then and this lies in the plane that contains the electric field and magnetic field, because E0 is the amplitude of the electric field. Therefore, the electric field and its magnitude both will be in the same plane. Therefore, E0 lies in the plane that contains E and B. It can be reduced into two components. Since it is a vector, E0 is a vector, it can be resolved into, any vector can be resolved into two orthogonal components. Therefore, E0 can be resolved into two orthogonal components. So here how we see a plane which contains E, therefore it contains E0. Now E0 is in any arbitrary direction. We resolve E0 into two orthogonal components. One component is in the horizontal direction, that is called EH. Then the other component is in the vertical direction, which is the vertical component EV. So V and H, the subscripts V and H, represent or indicate that the component is either vertical or component is horizontal. Therefore, using this, we can say E0 is equal to, in terms of vector, if we keep on writing E0, then E0 will be H cap. H cap is the unit vector along the horizontal direction. So E0 will be H cap into EH into exponential J phi H. What is exponential J phi H? It is the phase. EH is the amplitude of the magnitude along the horizontal direction, and the phi H is the phase of the component along the horizontal direction. So EH is the magnitude of the component along the horizontal direction. Phi H is the phase of the component along the horizontal direction. Similarly, along the vertical direction, V cap is the unit vector along the vertical direction. EV is the magnitude of the vertical component of the electric field, and V is the phase in the vertical direction for the vertical component. Now, from this equation in the right hand side, let us take J phi H common. If I take J phi H common, then the right hand side becomes H cap EH plus V cap EV into exponential J phi V minus phi H, because that is exponential J phi V divided by exponential J phi H, which is same as exponential J phi V minus phi H whole into exponential J phi H, where we can write phi V minus phi H is equal to delta, that is the phase difference between the vertical component and the horizontal component. The phase difference between these two components is equal to delta. So phi V minus phi H, that we can write as delta. And E0 we can write as the magnitude of the E0. As you know, if you have two components, one vector with two components, then each component square of the each component, take the square of the each component, root over of that gives you the magnitude of the vector. Therefore, E0 magnitude is equal to root over of EH square plus EV square. So now we are going to use this in our further analysis. Now let us write what is the electric field. Electric field will be equal to E0, a real part of E0, H cap E1 plus V cap E2 into exponential J delta. This we have seen earlier. Now you can ask me from where I have got this E1 and E2. That will be clear in a minute. But we know E is equal to real part of E0 into exponential J k dot R minus omega t. That we know. Now for the E0, we are writing like this: real part of E0, H cap E1 plus V cap E2. Because E0 we have written as H cap EH plus V cap EV. In that form we have written, so that we are rewriting it in another manner. Real part of E0 into H cap E1 plus V cap E2 into exponential J delta whole into exponential J k dot R remains as it is, minus omega t remains as it is, plus phi H, because we have taken phi H common in the for E0 we have taken phi H phase part common, if you remember the last slide. So from that we have got this phi H. So phi H comes outside. Now here we can say this we can rewrite as E is equal to real part of h cap eh plus v cap ev into exponential j delta, that we have seen just earlier, into exponential j k dot r minus omega t plus ph. This we have seen, and this one we have written as is the above equation. First equation is the same as the last equation. So this one, real part h cap eh plus v cap ev exponential j delta into exponential j k dot r minus omega t plus ph, that we have written as real part of E0. So what we have done is we have taken E0 common. So real part of E0 h cap E1 plus v cap E2 exponential j delta into exponential j k dot r minus omega t plus ph. Now what will be E1 now? If you look at this, then E1 will be EH by E0 into exponential j ph. E2 will be EV into EV by E0 into exponential j pv. Because we have taken E0 common, therefore E1 into E0 will be EH exponential j ph. E2 into E0 will be EV into exponential j pv. So this is what is E1 and E2. Now once we know what is E1 and E2, let us find out the relationship between them. So E1 square plus E2 square will be EH square by E0 square into exponential twice j ph. Now magnitude, if we are considering magnitude, E1 square will be equal to EH square by E0 square. E2 square will be EV square by E0 square. Add them together, so that will give us EH square by E0 square plus EV square by E0 square. That is equal to EH square plus EV square by E0 square. And we have seen EH square plus EV square is equal to E0 square, or E0 is equal to square root of EH square plus EV square. Therefore, EH square plus EV square is equal to E0 square. So E1 square plus E2 square is equal to E0 square by E0 square, which is equal to 1. So E1 square plus E2 square is equal to 1. So if I write E in this form, as a real part of E0 into h cap E1 plus v cap E2 exponential j delta whole into real part of whole into exponential j k dot r minus omega t plus ph. Then and the relationship between E1 and E2 and E0 gives us E1 square plus E2 square is equal to 1. E1 is equal to EH by EV into exponential j ph. E2 is equal to EV by E0 into exponential j pv. Now, how we know for plane wave, the electric field, the plane is perpendicular to the direction of propagation, and the plane contains the electric field. Therefore, the electric field is also perpendicular to the direction of propagation. The direction of propagation, along the direction of propagation is the wave vector k. Therefore, k dot E is equal to 0. This we have already seen when we discussed about plane wave. So for plane wave, k dot E is equal to 0. E has two components, EV and EH. So k dot EH is equal to 0 because EH and EV are in the same plane as E. Therefore, if k dot E is equal to 0, then k dot EH is equal to 0, k dot EV is equal to 0, and we have seen that EH and EV are vertical and horizontal component, which means they are perpendicular to each other. Therefore, EH dot EV is equal to 0. So these are all orthogonal vectors. K, EH and EV, these are all orthogonal vectors. Remember how we need to remember this. Then if they are orthogonal vectors, let us describe a new vector called the polarization vector. So this new vector is this part of when we defined E. In the E, you remember we have a part, a real part of h cap E1 plus v cap E2 into exponential j delta. that into exponential minus j omega t. This portion of E, let us describe that as the polarization vector. So polarization vector P is equal to polarization vector P is equal to real part of H cap E1 plus V cap E2 into exponential j delta whole into exponential minus j omega t. So here you can see that we have two components. One component is along H direction, horizontal direction. One component is along the vertical direction. So these two are in the space. Then the time variation is also taken, because we have said the polarization describes the locus given by the tip of the electric vector over one period, which means it describes the space and time. Time is over one period. So we have to take the time variation. Time variation is of the form exponential minus j omega. So that part we have kept. Then the space variation we have taken. Now, if you look at this, if we are describing vector P in this form, then vector P has two components. One is a horizontal component, other is the vertical component. So if I take the vector P, it will have a horizontal component which we can write as PH. It will also have a vertical component which we can write as PV. Okay. Now, what is the polarization vector? The locus of the tip is of this polarization vector has the same form as that of the electric vector, as that of the locus of the tip of the electric vector. So polarization vector we described in this manner. Then locus of the tip of the polarization vector, this we have also established now, that the locus of the tip of the polarization vector is the same as the locus of the tip of the electric vector. Why so? Because we have taken the vector part or the component parts of E, that we have taken as the vector part of the polarization vector. Since the vector part of the electric field is same as the vector part of the polarization vector, therefore their locus, the locus of their tips will be same. They will describe the same form. So here we'll take a break of 5 to 10 minutes. Then we'll come back and start discussing further.